All right, today we're going to do something a little different. We're going to get inside the head of a GCSE chemistry examiner. What's the plan? Well, we're taking a big, chunky 9-mark question from an AQA paper, and we're going to break it down piece by piece using the official mark scheme to see exactly what it takes to get full marks. And here it is, question 06, all about displacement reactions. You can see it's got a bit of everything: a definition, a pretty hefty calculation, an ionic equation, and a redox explanation. Now, a question like this, worth nearly 1/10 of the whole paper, can look pretty scary, but it's also a massive opportunity to bag a ton of marks if you know what the examiner's actually looking for. So how do you get every single one of those marks? Well, you've got to learn to think like an examiner. It's not just about knowing the chemistry, right? It's about showing what you know in the exact way they want to see it, and that's what we're going to decode right now. So here's our game plan. First, we'll nail the definition of activation energy. Then, we'll dive into the calculation, and I'm going to show you all 4 ways you could have solved it. After that, it's on to the ionic equation. And then we'll finish up with the redox explanation. And at the end, we'll tie it all together to really understand that examiner's mindset. Okay, first up, part 1, a nice, straightforward 1-mark definition. This is where being super precise with your words really pays off. And here is the answer, straight from the horse's mouth, the AQA mark scheme. See, the examiner is looking for one of 2 key phrases: the minimum energy needed for particles to react, or for a reaction to occur. That word minimum is the absolute key. If you just say something like the energy needed to start a reaction, you might not get the mark. It has to be the minimum energy. Okay, now for the main event, the 4-mark calculation. The question asks us to show that aluminum is the limiting reactant. That keyword show means we can't just say it's the limiting reactant. We have to prove it with numbers. But here's the great news. The mark scheme shows there are 4 totally correct ways to do this. We're going to walk through all of them. Before we start crunching the numbers, let's just lay out all the info the question gives us. We have the mass of our reactants, we have the balanced equation, which is crucial for getting the ratio right, and we've got the relative atomic masses we need for our calculations. Everything's right there. All right, let's go with method 1. The strategy here is to assume all the iron oxide reacts and then calculate how much aluminum we would need for that to happen. So, first step, we turn the mass of iron oxide into moles. Simple enough. Now, looking at the equation, the ratio is 2 to 1, so we need twice as many moles of aluminum. We do that calculation, convert it back to a mass, and look at that. We'd need 1.0125 kilograms, but we only have 1 kilogram. So we've just proven aluminum is the limiting reactant. Boom. Now, you can totally flip this on its head and prove the exact same thing. Let's try it from the opposite direction with method 2. This time, we'll assume we use up all of our aluminum and figure out how much iron oxide that would require. We follow the same process and we find we'd only need 2.96 kilograms of iron oxide. Well, we have 3 kilograms, so we've got more than enough. This proves that the iron oxide is in excess, which, of course, means the aluminum has to be the limiting one. Now, if you prefer working directly with masses instead of converting to moles and back again, you can use a proportion method. This approach basically combines all the steps from method 1 into one single calculation. You work out the mass of aluminum needed to react with 3 kilograms of iron oxide, and you get the exact same answer. You need 1.0125 kilograms, which is more than you have, so aluminum is limiting. And for our 4th and final valid approach, let's look at method 4. And as you probably guessed, it's just the proportion version of method 2. We calculate the mass of iron oxide we'd need to react with our 1 kilogram of aluminum. The result? 2.96 kilograms, which is less than the 3 kilograms we actually have. The iron oxide is in excess, so the aluminum is limiting. 4 different methods, same correct answer. So here's the most important bit. It literally does not matter which of those 4 parts you take. An examiner will give you full marks for any of them. What they must see, though, is your working. It has to be clear, it has to be logical, and it has to lead to a final statement that explicitly says aluminium is the limiting reactant. Don't make them guess what you're trying to say. All right, calculation done. Let's move on to the next part, which is worth 2 marks. We need to complete this ionic equation for magnesium displacing zinc. Just remember, with ionic equations, we're only interested in the particles that actually change during the reaction. And there it is, the perfect answer. You get 1 mark for getting the products right, the magnesium ion, Mg2+, and solid zinc, Zn. But the second mark, the one that people often forget, is for all the little details. That means you need the correct charges on the ions, and you absolutely need the correct state symbols. And for the final 2 marks, we need to explain why this reaction is a redox reaction. This part is a direct test of your understanding of what oxidation and reduction actually mean when we're talking about electrons. Before we look at the perfect answer, let's just quickly remember that super useful mnemonic OILR. Oxidation is loss of electrons, reduction is gain of electrons. If you can remember that simple phrase, you've got the key to this question. Now this is fantastic because it's a direct quote from the mark scheme. This shows you the exact phrasing an examiner is dying to see. Notice how it's structured. You get 1 mark for explaining that magnesium is oxidized because it loses electrons. You get the 2nd mark for explaining that zinc ions are reduced because they gain electrons. You have to link the substance, the process, and the electrons for both parts to get both marks. So, after breaking down that entire 9-mark question, what have we really learned about thinking like an examiner? What do you need to do to score those top marks? Let's quickly wrap up with the key takeaways.
Here's your checklist for success. First, be super precise with your definitions. Remember that word, minimum. Second, with calculations, show every single step. It doesn't matter which method you use as long as it's valid and easy to follow. Third, don't forget the small stuff. Charges and state symbols can be the difference between getting 1 mark or 2. And finally, when you explain redox, always talk about electrons.
And there you have it. You now have the blueprint for how to crack a really complex chemistry question. It's not just about knowing the stuff, it's about understanding how it's marked. This approach gives you the power to really target your answers and get every mark you deserve. So the only question left is, which topic should we decode next?